Mm. Okay, I guess we can begin now. Let me share my iPad. Yeah, so as I mentioned, we can definitely finish all the material for the class. I think by tomorrow should be fine. Um, because I don't want to kind of be covering too mm, a lot of stuff like too close to the final. So I'll try to say the most important things that are needed to be said by until tomorrow. Yeah, there are very few things left to discuss, so it should be fine. Uh, so today, in fact, like right now, there's only one really, really, really important thing left, which is like this use substitution method, which I was kind of doing yesterday a little bit for finding antiderivatives. So again, it is kind of like the version of the chain rule for integrals. So the idea is that when you were doing the chain rule, you would introduce a change of variables, which we typically called u. Now you're going to call this change of variables u again. So like the idea is like, it's basically two steps. The first one is to find like the change of variables u of x. Uh, that hopefully will make the stuff that appears inside the integral uh, look easier or more recognizable. And then in step two is to write everything inside the integral in terms of u. So for this, you need to use the following formula. You use that formula. So where does this formula comes from? It is what you would get if you divide it by dx, you would get that du dx is u prime of x, which we kind of know to be true because u prime is just like another name for the derivative. So it's kind of like it is the same formula as the expression for the derivative, um, just written in a slightly different way. But that's essentially what you need to use for these u substitutions. Well, let me see if I can give you some examples. And again, this does take some time to get used to because this u sub is, as I was saying, it's kind of like the chain rule, and the chain rule was like a complicated thing to work with in general. Okay, let's find. Okay, let's start with a bunch of. Yeah, I want to do a bunch of examples with this. Okay, yeah, let's work this one out first. So here are some examples. I'm going to try to make them in increasing order of difficulty. Okay. Let's say someone asks you to find the integral from 0 to 1 of the x divided by the square root of 2x plus 1. Okay? So again, whenever you have these sort of problems, the philosophy is to first find an antiderivative, meaning that you kind of remove the bound from here. So let's find first. So you try to find here this integral or antiderivative. It's also called indefinite integral. We trying to relate this as much as possible to one of the integrals I gave you in the table from before. So this table is super important. Where do we have it? This is like the key table for this part of the course, like just like knowing it. So of all the formulas that you see here, that one, which is the one that it resembles the most, it cannot be the stuff with trigonometric expressions because there's nothing involving sines or cosines or whatever there. There's also nothing with an exponential. Like 1 over x is also not there, but we do have a square root, and a square root has to be involves like a power of x, right? So really, like the one that you should be comparing this with is something like. So what you should try to rewrite this as is 2x plus 1 to the negative 1/2 dx. Is that making sense? So that is the closest way to write this relative to like the list of functions or the things I put on the table. Is that okay? And then but the thing is like if you look at the table itself, the table was given for x to the n, right? The problem is that we don't have x on its own here, right? It's kind of combined with 2x as 2x plus 1. So that's kind of where the chain rule idea comes in, or the use of idea comes in. You kind of just force it to become like x. So the way to do that is to call u 2x plus 1, okay? If you do that, then this gives you u to the negative 1/2, right? But then you still have dx, right? And so the x, the problem now is that you cannot have like a hybrid between u and x. So you have to change everything into u. So in order to do that, what you can say here is that if u is 2x plus 1, right? Then the u dx is 2, right? And then kind of use this equation to solve for the x. So you can say from here that the u over 2 equals the x. Is that making sense? And so that will allow you to plug that back into this expression. Is that okay? Any questions up to this point? But then if you use the formula, this is e to the 1/2 over 1/2. I mean, remember the formula is to add 1 to the exponent because it's the opposite of the derivative. So you increase the exponent by 1, so that gives you 1/2, and you divide by that same number. But what is u? U is 2x plus 1, so it gives you 2x plus 1. So what this is saying is that the integral of, or the indefinite integral of the x over root of 2x plus 1 is root over 2x plus 1 plus c over 2. Which again, what that means is that if you take the derivative of this formula, you will get the stuff in the inside. Is that okay? Is that making sense? But now we wanted this not for, like, we wanted the definite integral, right? So we wanted that this from 0 to 1, I believe. So what that means is that you're going to evaluate this at x equals 1 and subtract it at x equals 0. Okay, and so at x equals, as always, like these constants cancel out, so that should go away. And then at x equals 1, you're getting the square root of 3. And at x equals 0, you're getting the square root of 1. So this just gives you square root of 3 minus 1. That's your answer. Is that okay? Are there any questions about this? Okay, let's do another one. Let's see. Okay, let's do this one. Here's another example. So what could be a use of for this case? What do you think might work? Like many ways, again, like the philosophy we're trying to find a substitution is kind of to find something that would simplify how this expression looks like. So what's the most weird thing or the most complicated thing that you have currently in this in this function? What's kind of like the term that looks the most complicated one? Well, what looks the most weird is ln of x inside a square root. That's kind of difficult to deal with on its own. If we had square root of x, that wouldn't be a problem because that we know, you know, we kind of could compare that to the table. So the idea is kind of, again, to kind of try to force it into a version that looks more closely to the table. So you can take u to be ln of x. Okay. Right. You could, yes, you can rewrite this if you prefer as, I don't know if that helps to see what's going on, but yeah, you can rewrite it in this way. I mean, there are a couple of ways in which you could rewrite it. You also could rewrite it as 1 over x times square root of ln of x times the x. You see, there are a couple of ways to rewrite that expression. Is that making sense? Oh, but you cannot, right, but right, yeah, yeah. So, yeah, you can kind of separate the square root of ln of from the 1 over x. Yeah, yeah. So yeah, there are different ways. Like actually, you'll see this is the most convenient one to write it as. But yeah, there are different ways to have written this expression. And so what I was saying is that you should make u ln of x because if you do that, then du dx, right? When you take the derivative of this, you get 1 over x. But then if you multiply both sides by the x, you get that du equals dx over x. Is that making sense? So this thing that you had inside the integral becomes square root of u. And now you see dx over x becomes du. Is that okay? Is that making sense with everyone? And then after doing that, the problem is a lot more straightforward because it is u to the 1/2. And so this is, again, if you use the formula, it is add 1 to the exponent and divide by that number plus a constant. So this is 2/3 of u to the 3/2 plus a constant. So that's 2/3. What is u? U was ln of x, so it would be ln of x to the 3/2. So again, that's saying that, so what this is saying is that, the integral of ln of x, the square root of ln of x dx is 2/3 ln of x times 3/2 plus c, which again means that if you take the derivative of this quantity, you get that. So that's a way to check that you got the right answer, that you can always take the derivative of what you are claiming to be the antiderivative to check if you get like the function on the inside. Is that making sense? Are there any questions about this? Okay, let me give you two problems to think about first on your own, to see if this is making sense, and then we'll do them together. So here's problem one. So let's say I wanted to find this integral. For this one, I'll give you the hint, which is to just use u equals 1 plus e to the x. So I'm giving you the hint for that for this one. And for problem two, I won't give you the hint of what you should do. So, but hopefully, this is starting to make sense. So you have like an idea of what to use. So for the second one, you will also have to come up with your own use of. So try to do, okay. So try to do this one with this use of and try to see which kind of use of would work here. And then we will do them together. So maybe let me give you like, I think 6 minutes could be fine just for you, like you to think about them for for a bit. So let's just meet in 6 minutes to see how everyone is doing. Um, okay, so how did that go? Was anyone able to figure out the first one? What do you get on the first one? Is that okay? Is that what everyone found? Okay, good. And then what was the integral of 1 over u? Well, we knew the integral of 1 over x is natural log of x in absolute value. So it is the same, but just with u instead of x. So this is the natural log of u plus t. So this is the natural log of what is u? U is 1 plus e to the x. Now, not that you need to do this because already the answer is correct. That's fine. 1 plus e to the x is always positive. So in this case, actually the absolute value was not really needed. So you could, if you prefer, write it this way. But again, for our purposes, like both this way and this way are fine. Either works. Um, so that was the substitution for this one. Okay. And then what was the other one for x? I think that's the one that yeah, that's what I wrote. So, what's the substitution in this case? Any ideas? What could you try? Yeah, you kind of have to realize that the derivative of what you're saying kind of appears also in the inside the integral. So that's what's why it's a good idea to try that first. So if you start there, you get that. And then this one is rewritten this way. U to the negative 3 du. And again, you add 1. The exponent increases by 1 and then you divide by that. So you get u to the negative 2 over negative 2 plus constant. So you can write as minus 1 over 2u squared, but u was 2x squared plus q plus 3. Is that making sense? So that's the antiderivative in this case. Again, that means that if you take the derivative of this function, you will get back this expression. Oh, sorry. Yes, thank you. Good observation. Thanks. Let's Okay, let's think about this one. This is a similar one, but it's a little bit more complicated. So here's another one. And this is probably the last one I'll try to do for now about the substitution method. So here's another one. So let's say you wanted to find this. Okay. So what can we do here? What I'm going to call is u1 plus root of x. So what happens if I do that? So du over dx becomes 1 over 2 root of x, if you remember, right? And so that means that du equals dx over 2 root of x. Okay. Okay, and now this is where this is a little bit more tricky because we already know what to do with this term. It's going to become u. The thing is that the thing is that now you have root of x times dx, and that's not exactly what you have here because you see, like you don't have them being multiplied. You have them being divided. So we cannot do the same thing we have been doing before. Okay, but what you can say is that 2 root of x du equals dx. Okay, and this is kind of weird. Well, you can say, if you look at this change of variables, that is saying that root of x is u minus 1. So with that information, you can substitute root of x here and say that 2 times u minus 1 du equals dx. Is that making sense? This one is kind of confusing, so but is that okay? So again, the goal is to always write everything in terms of u. Uh, so what I did was kind of the fact that u is given in terms of root of x allows me to also give root of x in terms of u. So that's what needs to be done so that dx can be given all in terms of u. Is that okay? Yeah, this one does need a little bit of process and time to process to absorb what's going on. But once you do that, then what happens here? Root of x becomes u minus 1. Dx becomes 2 um, u minus 1 du. And at the bottom becomes u. Is that okay? So it becomes, after this, like it is just algebra, pretty easy algebra. You can take the 2 out of the integral. So it's like 2 times the integral of u minus 1 squared du over u. And then what you can do is expand this out. So you get u squared minus 2u plus 1 over u du. And then you should break this one into pieces. And this one, now each piece is easy to integrate. The first one is u squared over 2. The second one is minus 2u. The last one is plus 1 over, sorry, is natural log of u. And again, you can put like a constant at the end, somewhere at the end. So this gives you u squared minus 4u plus 2 ln of u plus c. And then you just have to put back in what u was. U was 1 plus root of x. And that one, again, that's the answer. That's correct. There's no need to put the absolute values in the inside the natural log because that's always a positive number. So if you want it, you can rewrite this as follows. Okay. So again, what this is saying is that if if you took the derivative of this, which is a lot bigger, if you took the derivative of this quantity, you will find root of x over 1 plus root of x, which it is harder to believe, but it just requires you to do some, like, simplifications. Like you have to simplify the derivative in this case to see that that's the answer. Is that okay? Is that making sense? This one, like, definitely is among the trickiest. Like, that's probably the top hardest type of use up problem because it does require some many steps. Is that okay? Is that making sense? Let's see. Okay, so again, for now, that's kind of what I wanted to say about use up. Uh, Now, and in terms of like tools to find integrals, that's kind of the last topic that you need to know in order to find integrals. The only stuff that's left is kind of like mini topics. So now we're moving towards like just smaller things. Um, so the first thing is like the average value of a function. So let's try to think about that. That's kind of like a nice thing to know. Okay. So let's start with something easier, which is how do you find the average value of a list of numbers? Okay, so you could think about one thing you could think about is your income, like for example, or like some money that you're saving or you're receiving each week, right? So let's say on week one, you have I don't know, you could get, let's just to make it easy numbers, $400. Week two, a better week is $2,000. week three, let's see, I want to do, now, let's say $600. And then week four, and not so good, not so great week. $200. Okay. So if you said well, maybe that represents like on each week what you received or what you spent or whatever, what would you say was like the average of money over that month, right? What would have been the app? Let's say this is like some sort of income just to make it more concrete, right? What would have been the average income on this over this month? Anyone? That's the answer. Or the average income on each week of each week. What will you do in this case? Yeah, like what you would do is add them all up together, right? So what you would do is do 400 plus 2000, right? Plus 600 plus 200. Uh, and then you divide that into the number, you divide it into the number of weeks because here we were talking about weeks. So you would do four, and that's 3,200 over four, and that's you know, $800, right? So that means like if someone had made $800 each week, they by the end of the week they would have made the same amount of money as you, right? Um, is that making sense so far so good? Is that okay up to now? So your average income, like you would, I mean, what people would say in this case is like the average income would be like $800 per week, right? The average income per week would be like $800. Okay. Now, uh, now I'm going to give you a slightly more complicated problem, which is like, let's say that with temperature, right? So usually when you check the weather apps or things like that, they may tell you what the average temperature for the day is, right? So let's do like a more interesting problem, which is to talk about average temperature. Right. And so, the thing with temperature is like, it can change from, say, one instant to the other, or from like you could think about it changing from 1 minute to the next, or from 1 second to the next. So actually, when you can think of the temperature, right? Like you can think of the temperature as a function that depends on time, right? So, for example, well, we're in the summer, so the temperature usually is pretty warm out there, right? So you could think, let me try to draw this for you. So you could think maybe here's 6 a.m. and let's do 9 a.m. Okay. So maybe like the temperature like at 6 a.m. is kind of warm, but not that warm. So maybe it starts at 70 degrees, 17 Fahrenheit, right? And then it just like it starts warming up, warming up, warming up. And then maybe some clouds came, and so it's got slightly cooler, and but then the temperature keeps increasing, right? Is that making sense? So the temperature in general, like you would just think about it as like a function that changes over time, right? But then you could ask, well, what do you mean then by the average temperature, right? It's less clear here, okay? So yeah, let's say, okay. So what we're going to do to attack this problem is kind of to deal with a slightly simpler version of the problem. And well, let's say that this got up to 90 degrees. So the temperature between 6 a.m. and 9 a.m. went from 70 to 90 degrees, but it did some fluctuations, okay? Um, so what we're going to do to attack this problem is just kind of to break it up, you know, break this number, break this into pieces and do a little bit of um something slightly easier. So instead of thinking about it as the temperature going from 6 to 9 a.m., let's just break the time into chunks of 30 minutes. Okay? So here's 6:30, here's 7, here's 7:30, here's 8. Oops, I need a little bit of space. Here's 8:30 and here's 9. Okay? So now what I'm going to do is like I'm going to analyze the temperature, right? Instead, like I'm going to kind of record the temperature every half hour, right? So, um, so for the between, what I'm going to do is like between 6 and 6:30, right? I'm just going to pretend that the temperature was constant, okay? So let's say, and then between 6:30 and 7, I'm going to pretend that the temperature was constant, and then, oops, let me put it here. Between 7 and 7:30, I'm going to pretend the temperature was constant. Then between 7:30 and 8, I'm going to pretend that the temperature was constant. Okay. And then between, let's see. Let me see if I'm putting this correctly. 6:30 is here. Yes. Is that making sense what I'm doing? So I'm kind of pretending that instead of like working with all these values for the temperature, I'm just going to divide these 3 hours, right? How many hours do we have here? We have 3 hours. So I'm going to divide them into 6 intervals of 30 minutes, right? So 1, 2, 3, 4, 5, 6, right? And on each interval, I'm going to pretend that the temperature was constant. Is that making sense? Kind of like the philosophy. So for example, on this first interval, maybe the temperature was 70. On this second interval, it could look like maybe, let's say, like 82 degrees. On this third interval, maybe let's say it's like um 86 degrees. On this one, it would be like what? 82 again. Let's say in this one is like um 85, and then this one is almost, let's say it's almost 90, so let's say it's also like 88. So like I'm going as an approximation for what I mean by the average temperature. I'm just going to add up all these temperatures and divide it by 6 to get like a rough estimate of what the temperature was. Is that making sense? So like an approximation for what the average temperature is would be 70 plus 82 plus 86 plus 82 plus 84 plus 88 divided by 6. And well, let me put it do it on the calculator to see how much I get. Um, so this gives you 492 over 6. Oh my God, I cannot believe I chose the correct number. I didn't have to approximate it. I'm happy this worked. So in this approximation, you would say that the average temperature was 82 degrees. So is this making sense so far, so good? But now comes the key point of view, which is what would come next? Like, what would be the next question? I don't know if anyone wants to has like an idea. What would be a better approximation for the average temperature? Maybe that's how I should ask the question. What would be a better way to compute the average temperature? So a better way would be to say why did you break the time in chunks of 30 minutes, right? There's nothing forcing you to break it into chunks of 30 minutes. Maybe this would be a better approximation if you broke the time intervals into every 10 minutes, right? Or every minute. Is that making sense? So if you do the same, if you apply the same principle to smaller time intervals, you would expect that to be a better approximation for the temperature, the average value of the temperature. Is that making sense? So what I'm trying to say here is that like what you can think of doing is that you had like the temperature, right? Let me see if I can try to copy this again. You had like here 6 a.m., you had 9 a.m. But what I'm going to break it now for is like in n pieces. So I'm going to break this into 10 intervals. Sorry, n intervals. Before we broke it into six, right? We broke it into six intervals. This one, this one, this one, this one, this one, this one. So now I'm going to break it into n intervals. So now I'm going to have n intervals of the same size. Okay. So that how much each interval lasts. So each interval lasts like what? Uh, 3 hours over n, right? And let's call that time interval delta t. Is that making sense? So when I broke this into 6 pieces, each interval was 30 minutes, right? But if you break this into more pieces, then the intervals would be shorter, like the time intervals would be shorter. And so what you end up getting is something that looks roughly like this. Oops. So now you have like a time T1, T2, T3, T4, up to Tn. And so now you're saying that the average temperature should be the temperature at time T1, but plus the temperature at time T2, plus the temperature up to time Tn divided by n. So it's kind of like the same that we were doing before. I'm just taking an average of the temperatures, but now there are like n temperatures to choose to think about, right? And different values for the temperature. Is that making sense? And we're almost there. So um how can you think about this in a more useful way? Well, if you look at this, this this also gives you like the formula for n. You can say that n is 3 hours divided by delta t. So another way to think about this formula is that you could decide first, like how far away, how long do you want your intervals to last, and that determines in how many pieces you had to chop up the interval. So this also, if you plug this into the formula, this would give you T of temperature at time T1 plus the temperature value at time T2 up to the temperature at time Tn. And what is n? N is 3 hours over delta T. And so by the properties of the fractions, you can move this to the top. So this gives you, let me write it in a way that's convenient. It's 1 over 3 hours times temperature T1 plus temperature of T2 plus temperature of Tn times delta T. And now what I'm going to do is to distribute this. Okay. So why is that useful? What do you think this means? For example, what does the temperature times T1 times delta T means in the graph that we had? Can anyone think about what that means? So here's the temperature at time T1, right? Oops. Here was the temperature at time T1. Uh, and here's delta T. I mean, I think okay, it's looking a little bit weird. Here's the temperature at time T1. I guess what I'm trying to ask is what is the area of this rectangle? It is the base is delta T because that's how much each interval lasts. And what is the height? The height is T of the temperature at time T1. Is that making sense? Because like the temperature is how high you are on the graph. Maybe it's more clear in this picture for the second one. So the base of this rectangle is delta t because that's the amount of time on each subdivision, and the height is how much the temperature is. Is that better? I don't know. Is that better? Looks better. So like what I'm trying to say is that these are like kind of areas in the picture, in the graph, these are actually like areas of rectangles. Is that making sense? So so really what we're doing here is like a sum of areas of rectangles, but that's precisely what we knew how to do before because that's essentially what the integral is for. So just to make this story short, because I already kind of spent a lot of time giving you the motivation. The motivation is actually to define the average value of the function as the integral divided by the total time or total length of that interval. So let me give you like the definition finally. So the idea is that if you have a function of one variable, if you have a function y equals f of x defined on an interval, a comma b, its average value is, let's write it like this. The average of f is 1 over b minus a, because that's the length of the interval, times the integral from a to b of f of x dx. Okay, so the average value is just essentially the ordinary integral divided by the length of the interval. So it is not that different from what we have been computing, but it is useful to understand why this can be regarded as an average value. Is that okay? Is that making sense? So just to give you, I mean, again, like the average value examples are not too difficult because they're really just the same they're really just the same problems we have been doing. It's just at the end of the problem you divide by the length of the interval. So let's just do, I mean, really the problems are quite straightforward. So let me just do an example for you. So so example, find the average value of f of x equals x squared from on the interval 1 to 3. So the average value is like, again, it's essentially you find the area under the curve and divide it by the length of the interval. So the average of f of x is just x squared dx, but here is from 1 to 3. And then you divide by 3 minus 1 because that's the length of the interval. Or let me write it like this. So what's x cubed over 3? That's 27 cubed plus c minus 1/3 minus c. Sorry. Right, so here I'm evaluating at x equals 3. This is what I get at x equals 3, and this is what I get at x equals 1. Is that making sense? So that's the average value. So here's how you can think about it. just to make this more intuitive, here you have y equals x squared. We are looking at the interval 1, 3. So here's 9, and here's 1, right? And so what is 13 thirds? That's what, like 13 thirds is like 0.40. Yeah, okay. 13 thirds is like 0.43, 0.33, sorry. So you see, like the point that's in between midway of 9 and 1, the point that's in the middle between 9 and 1 would be would be 5. Let's see. But yeah, so the idea is like that okay, this is a fun example. So there's different ways to see it about it. Yeah, the thing is like the function, the thing is like the function x squared, like if you didn't know, how should I say it? If the values of the function were changing at a uniform rate, right? If the values of the function were changing at a uniform rate, then you would expect like, oh, maybe the average value is 5, right? The thing is like the way in which x squared takes values is varying with x, right? Like, you know, so it is not that like the values of the function are increasing at the same speed. In fact, that's being controlled by the derivative. So that's why the average value ends up being different from like just like the midpoint from between 9 and 5, for example. You see? So that's kind of the idea here. So it's kind of like it is kind of not at a uniform rate that the function is changing its values. So that's why the average value is just not the midpoint, or it's not equidistant from the two values that the function takes on that interval. That's what I'm trying to say. But that's more like for interpretation. Like in practice, like, finding these average values are not it's not too complicated. In fact, let me do another one. Which is fun to do just for. So here's another example. Find the average value of a constant line. Okay, so we want to find out the average value here. So let's see. So the average value of f of x is always 1 over b minus a times the integral from a to b of f of x dx. Okay, that's a that's the definition of average value. But now the function just happens to be mx. If you remember, the slope for a line is constant, so you can take out the slope. And this gives you x squared over 2 plus a constant evaluated at x equals a and x equals b. So that gives you, I mean, again, the constants of integration cancel out, so you get b squared over 2 minus a squared over 2, right? So you get m over 2b minus a times b squared minus a squared, and then you get b minus a times a plus b over 2b minus a. And this gives you a plus b over 2. Is that making sense? Like maybe I should stop because I may have gone a little bit too fast. So again, this isn't easier to interpret because this is saying that for a line, on a line, like kind of like the values of x are increasing, changing. Sorry, the values of the function are changing at the same speed. So what this is saying, this is saying is that the average value for a line is literally like maybe I should write it like this, right? Yeah, I think this is more intuitive, clear if you write it this way. What I'm saying is that the average value in the case of a line is literally the average of these two numbers because on a line, the rate of change is constant. So the function kind of spends the same amount of time uh, on each value of y. So that's why the average kind of just ends up being the average between the bottom value and the top value. But something like a parabola where the function's kind of like is changing its values at different rates, that is not necessarily true. And that's why you need to do the calculation to see what the answer actually is. Is that okay? Maybe I think this is a good example just because it helps understand that better, a little bit better. Is that making sense? Okay, so yeah, so there are only like two more things that I need to tell you before finishing all the topics. So let's do that tomorrow because I feel like we have covered enough material today. So if anyone wants to ask me something, I'm happy to stay longer. Like if you want to talk about it right now, if not, feel free to to go. But since we have some extra time, I can. I want to talk. I'm happy to. Do you have any questions or are you doing good?